week 11 of stochastic control and communication. So, we'll quickly recap what we talked about in last week, and then we'll start with this week's tutorial. So, last week we talked about the Witzenhausen's problem and the variants of Witzenhausen's problem specifically, and the focus was something called the dual effect. And dual effect was something that meant that the policy of controller 1 obviously affected the cost, but at the same time it indirectly affected the policy of the second controller also. Because of these two things happening, and because the information structure of the problem was non-classical, it became a complex problem to solve. And we had talked about one particular um, one particular policy, one particular actions that he had given, which basically were not linear, but they were able to perform better than anything that would have been person by person linear for both, suggesting that linear strategies will not be enough in LQG games with non classical information structure. So, it was the information structure that was very important in this scenario. Um, while we were talking about Witzenhausen's problem and various types of controllers, we also said that these problems can be interpreted in a slightly different way. We don't have to always think of one controller taking actions at different point of time. It can be multiple controllers taking actions at certain points in time. So today that's the part that we're going to focus on. We're going to mostly be talking about team games or stochastic control where there are multiple agents taking actions. Um, if you've gone through the lectures, you would have noticed that Sir took one example and showed what happens to different information structures in this type of a game. And then he talked about one more special class of problems where certain interesting properties show up. So I'll quickly just brush up what was done in class and then directly go to examples. So now we are thinking of the regime where there are n agents. Each of them, each of those n agents receives some information which is yi of t, where I refers to the agent and t refers to the time at which the information was received. Then things like noise, initial state, all of those are clubbed together and they're put in this environmental noise. Basically, this is the quantity that we cannot control, in the sense that we cannot control the distribution of this quantity. It is something we just directly get. So, this yi, the information we receive, would typically be some sort of a function of this environmental noise and the actions taken by the agents. U here refers to all the actions taken by agents at different times and by each of those agents. So here each of these u1 refers to at time t equal to 1 what are the actions taken by all of them. So it's the full tuple of nt n times t actions, which is what is being referred to as this small u. And recall that the action itself, any one of these actions, right, for example this one, or any action of the ith agent at time t, would be something which will be a policy of whatever information he has at that time. And this has to be such that causality is satisfied, meaning if an action has not been taken yet, that information cannot be available to any agent before the action has even been taken. That's pretty much what it means. Like something that has not even happened, information of that cannot be available to anyone. So that's the meaning of causality being satisfied. And another thing is that we're restricting ourselves to sequential problems or problems with a fixed clock, meaning where at every fixed time step, an action is to be taken. When to take an action is not a random variable. So, time is not a quantity that can be uh, made random in the whole problem. Here, it's like a fixed clock, and at each time step, some action needs to be taken. Okay. So, ultimately, in all of this, what happens here is we refer to this quantity, the function eta of ti for all I and all t, as the information structure, and whatever properties are satisfied by this, that becomes the description of the information structure. At this point, we don't need the kind of information structure we had before. We're no longer going to refer to this as classical or non-classical. That will happen on its own. Here, a different kind of classification happens. So first classification is what is called as static team games or static team, where the information yi of t only depends on the noise, and it does not have the information about the action of the other agents. It would know its own action at a given time, but not the actions of the other ones. And this is something which is commonly also observed. One of the examples that Sir gave in the video was of wind turbines, that each action will depend on whatever information is available about the whatever parameters that describe wind and weather in locality 1, and similarly action for locality 2 will depend on the weather condition and wind parameters in that locality. Overall, the information yit and yjt might be present in it will be present in the environmental noise itself. So it will be some component of the environmental noise that is coming out and being made available to both the agents. Here, this while taking an action here, this wind controller doesn't need to know what action was taken by the other wind controller. It's that kind of a setting. Okay, now we can think of the n agents acting at t times as there being n times t agents, because they don't need to know about each other's action. It's individual information, individual actions that at individual time they have some other information. That information may not be even related to what they had known before. So all of these can be treated as separate agents itself, meaning this just can be thought of as n times t agents. And since we have already absorbed time in the number of agents itself, time here has no relevance. That's the reason why this is called a static team. Okay, so far?
This one question I had.
Mm-hmm.
Causality, suppose we have prediction algorithm like Kalman, we are predicting the next time and then we are taking innovation equation.
Mm-hmm.
So causality, to define the causality, is the prediction okay or prediction also not? Because when you predict, we know what is going to happen.
Prediction is an estimation, right? Prediction is not the actual action. It's not the information about the action of the other guy. It's just a belief of what you think they would have taken.
Okay.
See, if the situation was that, for example, if it was a game and you had the game matrix available to you, you would be able to tell if the agents are trying to optimize in a certain way which action they would have taken. But that doesn't mean you know which action they took. They might choose not to take that action for reasons that may not be clear.
Okay, so it's
So,
only for the
yeah, we're
set
talking about
action.
complete information that this action was actually taken up till this point of time. That information is not available. If that is the scenario, we call it static team.
So basically,
Belief is
prediction is
okay.
allowed.
Prediction, estimation, belief, all of those are fine. Because
Okay.
you will most likely be making those things. You will be making some estimations to move further. If it's needed. In certain problems, it might not even be needed at all. Okay.
Okay.
Right. So, okay. So the other kind of games would be where there is one agent for which he knows the action of the other ones, or maybe he knows the action of one or two of the other ones, something of that sort. In that scenario, such a team is no longer static, it's a dynamic structure. And even if we have a problem with even if we are dealing with a problem with static team, the solution itself is not going to be trivial, and we'll see how the problems from LQG or LQ with whatever noise they have with classical information structure, they have static team behavior. In fact, this is something that we already saw as an example in one of the tutorials. We took an LQG team game and we talked about it already. Anyways, nevertheless. So, point to remember here is there are two things. Depending on what kind of this what kind of eta is being taken here, there are two scenarios. So, eta t of I, if it depends only on the state of the world or the environmental noise, then that is called a static game or a static team. On the other hand, if that's not the case, if the action even if the action of only one extra person is known and the one other agent is known, it's no longer static, it becomes a dynamic team. Okay, so today the focus is on team games. So to illustrate what kind of things happen here, what happens to information structure in this, there are quite a few variations still possible. How are those dealt with? So in the lecture, sir took an example. He took a very simple static game, and then he talked about what happens if there is perfect information versus if there is oh perfect information and identical, meaning they can distinguish which exact value of xi it is. Imperfect, another possibility is imperfect and identical. Identical would mean both the agents have the same information, but they don't have complete information, meaning um, from the three state of the world, maybe they can't distinguish two of them. So maybe they can't distinguish omega 1 and omega 2. If they can't distinguish all three of them, that is also imperfect only, but that's a very minor case. That's more like having no measurement whatsoever. So these two previous cases, the case with imperfect and identical measurements or the case with imperfect information, both of these can be thought of as just there being just one agent taking the actions, because it doesn't matter what they're doing. The policy can be clubbed. Because of that, it reduces to just a one agent problem. Another possibility is if the measurements are not identical. This is the one which is slightly more interesting. And the last one is non identical and non trivial. So, what we're going to do now is we're going to take another example. There's no point going over the same example again. We'll take another example with simpler numbers so we can do the calculations on the fly quickly, and we'll go through these cases again. if you have any doubts, you can ask there, and that will anyways clear out if you had anything remaining from the examples from the videos itself. Okay, so the examples are here. Okay, so again we have two agents. For them, the actions are, for agent 1 the actions are U and D, and for agent 2 the actions are R and L. The noise component has three possible values, each having some probability, and these are the cost. And the objective here is to minimize the cost, and we're supposed to do it for all of these cases. Because the costs are actually quite simple because of the presence of zero and everything, this is quite easy to solve. Okay, maybe we can make it even simpler. Okay, maybe let it be. Okay, so let's take each of the cases one by one. uh, so we will start with the first scenario. Okay, perfect and identical information means they know who did what. So the choice is just choosing the best action. So there are more than one possibilities. So one of the possibilities where you would get optimal, I'm writing it as gamma 1 gamma 2 given the common information they have. So if it is W1, UL is one possibility. Then for omega 2 it is DL. And lastly, for omega 3, there are again two options. I'll go with DL. Now recall what we're supposed to do is for a gamma 1 gamma 2 pair, we need to find out the expectation of gamma 1 of y. Here y just refers to being able to distinguish all of them. So what would you get in this particular scenario? This is one of the optimal policy.
But we have many optimal solution, right? Like UL and UR.
There are Next question I was gonna ask was, tell me the number of optimal policies, because there's more than one.
Okay, so you choose one, so numbers are same, we can
Yeah,
plug in.
yeah, exactly. So this is one of the optimals. I'm not saying this is the optimal.
Then cost is zero.
The cost is zero. Reason being, it's 0 times probability of W1 plus 0 times probability of W2, and again 0 times probability of W3. That's why it ends up being 0. And yeah, now tell me how many such optimal policies are present in this particular example.
So, okay, two possibilities above, one and two is there. So permutation combination we need to apply.
Mm.
2 and 3. I think 5.
That's
5.
not how you're supposed to do it.
Okay, optimal policies based on that.
The optimal policy is for all the three different values of
The
y,
omegas or the
right? So you have to consider the whole bunch.
okay, okay,
This is
got
one of them. Another would be if for W1 this is what you chose, for W2 and W3 you let it be the same thing.
then four
That's 2,
possibilities will come.
right? Then instead of this one you could change to the other one. Exactly. There are 4 optimal policies. This is just one of them. If you want to write down all of them, they will be for W2 it is fixed. For W1 there are 2 possibilities, and for W3 again there are 2 possibilities. So you just have to take those. So the case of finding the optimal policies and the optimal cost for perfect and identical information is fairly straightforward. It's fairly easy. Any doubts in this part? Okay, then let's try. Now let's try the second scenario, which is imperfect and identical information. So there are a few cases possible there, right? One could be the common y1 equal to y2 could be they cannot distinguish between omega 1 and omega 2, but they can tell if it is omega 3 or not. That's one possibility. Similarly, there can be two more possibilities here. So now let's look at each one of them. So we're considering this scenario first. Let me paste this below, otherwise it requires scrolling up and down again and again. Okay, so this time the policy would be, again I'm writing it as gamma 1 gamma 2 together for a given y, because the observations that they're making or what they can see, the information that they have is same. This is still a valid thing to do. So this would be some pair here, some AB here, some CD here. So first of all, how many such possibilities are there?
Tuple possibilities.
Huh?
A tuple possibilities, right?
No, I'm okay. So let's put it this way: how many total policies are there if I'm writing it this way? So let's consider this as some gamma tilde. The pair gamma 1 gamma 2 is what I'm referring to as gamma tilde. So now, how many total such policies exist? Total policies. Or okay, uh, this refers to,
Is it 16?
how exactly is it 16?
Because you keep A constant and vary all. No, you A vary A and you keep everything constant. B, C, D constant, vary A. So A has two possibility. Then you keep B varying and A, C, D constant.
No, but okay, let's think about it this way. So for each agent, for agent 1, it has action U and D available to it. And agent 2 has action L and R available to it. Right? Gamma tilde would be like a Cartesian product of these two. That's what we're getting. That's the tuple we're getting. And we have gamma is having two different values. So how many policies are there for each agent, and then maybe we can talk about how many policies are there overall.
Each agent we have two possibility. Straightforward.
No.
Each agent
So okay, it's this way.
include
Each agent can choose U or D for each value of Y. Meaning there are 2 to the power 2 policies for each agent.
how.
So what you were saying 16 was actually correct. It just hadn't given the correct argument.
Okay, because I was thinking keeping A very rest are constant, something like that logic.
Mm. Because you, okay, it actually did work, huh? ठीक है. So there are total 16 possibilities, and out of those 16, we're supposed to find the one with the optimal cost. So
So
one
basically,
option is to go through all 16 of them, but is there a quick thing here, since we can see the cost function is quite easy to handle?
wherever the zeros are coming, we can track that how many zeros cost, because we know that zero is minimum, and if we track how many places zero would be, that many optimum policies. Like maybe some other method possible.
It won't be straightforward. See, what is happening here is the two agents cannot distinguish between omega 1 and omega 2. For them, this is one bunch, this is the other bunch. And for this bunch, for W1 or omega 1, the action which is suitable for agent 1 is actually U. But here the suitable action is definitely D. If you want to compare, we can clearly see L is the right choice for agent 2, or yeah, for agent 2, that is fine. But that then again, if agent 1 has chosen U and agent 2 chooses L, but they are in W2, they'll incur a cost of 2 times whatever is the probability of getting omega 2, which is. So the only solution in this scenario is that we need to make the table, and there's no shortcut possible. So let's do that. The shortcut would have been possible if the information structure was different, but that's not the case here for us. Okay, so since there are 16 of them, I'll write it like this. So I'll write the pair as AC or BD. Okay, AC refers to action taken by agent 1 in the two scenarios, and BD refers to the action taken by the agent 2 in the two scenarios. Okay, so here the possibilities are UU, UD, DU, and DD. Uh, One second. Here the options are LL, LR, RL, and what was the option? Remaining RR, right? So we need to evaluate for all of them, but we can try and do it only for the cases where we think there is a possibility of getting the optimal. In principle, we should be doing it for the whole thing, but it might still work if we do it just for a few cases. Okay, so let's focus on this. Since both the agents can figure out whether it's W3 or not, they can choose the best action here quite easily. And the best action is either DL or UR. DL or
Is this argument valid for all?
see, for this particular case, it'll actually work quite easily. Reason being, you have everything positive.
Correct.
If you had even one negative number, then you can't say it.
Mhm.
Here, we can see it very clearly that this is something known to both of them. So, the best one will definitely be something where this is as minimum as possible, which is in these two scenarios. On the other hand, the ultimate optimal will depend on what happens to these two and also the probabilities. And since the probability for omega 3 is not the smallest, it still would be fine. Let's see what happens and then find out. So, our job is to identify the ones with du. So, the ones that may be of interest are the following: D and L. So, this is one possibility, and D and L. The other is right. Again, this also. It's still quite a few things to look over. U and R. U and R. But our job is at least reduced to half of what we would have needed to do otherwise. Okay, so let's consider this one first. Hmm. What will be the expected cost here?
Point 8 coming. It's coming point 8.
Uh, U. So UL and UL gives you 0 times point 0.2 and 2 times point 0.4. Oh, okay, that's why. And LR gives you this. Okay, that's again 0. So this is coming out to be point. Okay, so this is point 0.8. Let's try filling the remaining. Okay, let's try this one. UDRL
Same point it coming.
with UR it's 0, with UR it's 0.8, with DL it is 0. Okay, right. So this is again 0.8. Not helping. Okay, let's try to use a strategy or some
I'm
policy
believing that
which focuses on
DULR
this.
is the optimal point for is coming.
Hmm?
DU and LR.
DU and LR. DU. So it's DL. Right. It's gonna be, because of this it'll come out to be zero point 0.4. This is anyway 0. DL.
Yeah, basically I just maximize the number of zero possibilities. So DULR has highest.
Hmm.
I'm trying to think all three zeros somewhere I'm thinking. But
DU LR. Right. This is one of them. There should be one more with the same value. Anyways, so if you do the whole process, this should be the best one. Uh, yeah, this one. My guess is there should be one more.
I think DDLL.
Um, hmm. DDLL is again zero point 0.4. DDLL. Right. Ah, DR will never work, right? DR. Wait, that'll not work. Okay, so this is with the first kind of information structure that we are choosing. This one. Remember, there are other possibilities. There were the other versions that we wanted to see. The other scenario was you can fill it up and it should come out to be zero point 0.4 itself. Um, the other scenario is when y1 and y2 are, the dependence is on, let's say, 1 and 3.
But just a curiosity, like all information structure, we have same cost table, right? And it's identical. Isn't it the optimal policy and optimal cost should be same, all three, because of identical structure.
Which one are you talking about?
Like this existing one, we solved one problem where
Right.
omega 1, omega 2, and omega 3. So omega 1, omega 2 are compressed, or that information is non-identical. Like I can't
See,
identify this
okay,
news.
I'll answer that. So, here in this first scenario, we knew W3, meaning both the agents were definitely choosing the optimal here. Only
Mm-hmm.
then they'll get the overall optimal, otherwise, they will not get the optimal. If you want, you can verify for anything else.
Mm-hmm.
Right? Similarly, now what they know for sure is omega 2. So now their choice is different. Now, because it's omega 2, this choice is fixed. DL is fixed. Now they just need to find out what should they do for omega 1 and omega 3. What's the best that they can do? Because for those two, it's going to be the same actions. But there are still four pairs of actions.
Mm-hmm. Okay.
So even though the table is same, what gets filled and which will turn out to be the important ones is not going to be the same. So now, just by observing it carefully, you'll be able to find out what is the right answer. Just observe the table, observe the utilities very carefully, and remember right now W2 or omega 2 is known to both of them perfectly. They don't know the difference between omega 1 or omega 3. Is there a policy that is best for W1 and W3 both? Did you follow what I'm saying?
Yes, I'm listening. I'm thinking about
Mm.
this is okay. So as of now, omega 3 was distinguishable. Now omega 2 is distinguishable.
Hmm. Now this is separate. Here we'll choose whatever is the best one, and the best one here is DL.
Correct, correct, exactly. Now I need to just we need to figure it out somehow unknown part and connect with the previous table. But it's not coming because I'm seeing all 16 possibility you enumerate for one case, and somehow if there is a connection established, all information structure.
The table will not fill to be the same.
Hmm.
See, remember, when I wrote them as UU, I meant the first one is the scenario when Y is omega 1 or omega 2, and the second is when Y is omega 3. Now the scenario has changed. It would look the same, but this is the extra information that we're not necessarily writing. So the numbers may or may not match.
That's it. I'm just saying because probability is same, table is same, so numbers will match, but position will differ. That's what.
Okay, let me show you something. I'll not fill the table. I didn't bother filling the previous table. I'll not fill the table here also. But it will be a table definitely. So just for ease, I'll copy this table. But the ones that were important in the previous one may not be important here.
Correct, correct.
Right? So let's first identify the ones which are important here.
Okay.
Ugh, that was a waste of time. Never mind. I'll just make it again. Okay, so we have
Mm-hmm.
UU, UD, DU, and DD, LL, LR. So these are all of them. Okay. Now, see, this is my claim. For the second one, see, the first one refers to omega 1, y being equal to either omega 1 or omega 3. And
Correct.
y2 equals to y equals, here the y equals to the situation where it is omega
Omega
3.
2.
Sorry, right, omega 2. Right. Correct, good catch. So, this is what we should be focusing on, the scenario where this is D. So, this one here or here, and these ones. So, now there are just the following possibilities. 1, 2, did you understand why I'm saying that? If you want, you can compare. The possibilities ended up matching,
Mm-hmm.
right? In the first scenario, we had more options from which there might be the optimal one, but here we are certain that won't happen. So now what I can do is I can look at all of these, and I'm actually not going to even look at all of them. The answer is much easier for this particular scenario. Consider this: J U R. Consider UDRL. When
It's
you
zero
choose,
completely.
hmm?
It's complete zero.
Exactly. Can you get something smaller than that?
No.
That's it. That's a justification here. If you had something negative in the cost, then
Mm-hmm.
you'd have to do the whole thing, because then you don't know what will happen. There might be situations where it cancels and it might have an effect. So there you'd have to be slightly more careful.
Those fine, we can shift them to positive sign. It's very strange now. I'm very surprised because I was estimating like some kind of position change will happen. Because previous table there is no zero. There's no zero at all coming. Here it's possible.
Mm. See, that's the key point here. They have partial information, but what they have matters, because what they are able to see could be of something that they can use. So notice the reason why it's happening like this. This is a illustrative example. In fact, the example in the assignment is very similar. I actually just changed the number, something else. So notice what is happening here. When we did it for perfect information case, we said there are how many? Four optimal policies. In the case of omega 1, there were two options: UD and UR. Two options. Just one option here. Here again, two options. And notice these two options are so well aligned. That's not the only thing. They refer to the exact same actions by both the
Okay.
agents. This is a rare case. This will generally not happen. Generally, you will have to solve the whole thing.
Mm-hmm.
Okay, now we're repeating the same process with the third information scenario. The third scenario now. Copy some of it and then make the changes. So now in this scenario, we have one is separated, 2 and 3 are together. We can repeat the same arguments as before. That be UD, DU, and DT. These are the policies. For the other agent, it is LL, LR, RL, and RR. Now, what do we know for sure? We know omega 1 for sure. Both of the agents know it for sure. Meaning they'll choose what is best here. This they can choose for sure because they can see it. If the information is visible, they'll make the best choice. There's nothing to think. So they will either choose this scenario UL or UR. Either way, agent 1 will just choose U. And let's say now I'm writing it the following way. This refers to y equal to 2 and 3. Okay, and this one refers to y equal to omega 1. So it's omega 1 known and not known. So making it clear what I mean and what is where. So I am only interested in the scenario when this index is U. So it's here and here. And the second index for the other controller or the other agent can be L or R. Nothing of a problem there. So what we ended up choosing is this. Actually, the kind of arguments I'm making right now, they sound vague, but they're very similar to the kind of arguments you'd see in game theory when people talk about dominant strategies or removing dominated strategies from the game matrix. That's roughly what I'm doing here without making it more clear or anything.
Okay.
Because of presence of zero, it becomes much easier to handle. That's pretty much it. Hmm. Now, can you identify what would you be doing in this scenario?
Something regarding I need R.
See, we already made up our mind about how to handle this one. This is done. All we are left to do is figure out these two. What's the best out of these 8 options?
So D should be there. So third row you can choose. Like
Okay.
above first row you can delete. You
Okay.
don't need.
Okay.
Why? Because the D value for both cases are 0. So in the unknown scenario, like in the omega 1, omega 2, either of cases, if we choose D, you will be well off
Hmm.
than all other cases.
Hmm. If you've
So
already
that
chosen D,
nice. Then
what
L
should
is
you?
pending. Wow.
That's it. That's why I was saying this is a very clean example. So
Okay.
what exactly would it refer to? It's D U and oh, which one? Hmm.
It doesn't matter. LL and RL both will work.
Will all the four of them work?
DU, then definitely you will get 0 for the this side. Now LL. Okay, no. This side L. I think it will work, right? LL.
Okay.
LL perfectly work.
Are you saying this whole row works?
No,
No.
no, no, no,
No,
no.
right? Huh.
Not all.
Okay. So
The
tell me
LL.
which ones in this row will work.
DU LL.
DULL.
Yes.
DU. Uh, LL. Yeah, this definitely works. What will be the value?
0.
Exactly.
And then second will be uh, DU
Hmm.
LR.
Right. This can be R. This one has to be 0. The first one has to be L.
L.
Right.
Perfect. So this one only, like anything connection with D with R goes off. It's not zero.
Exactly. So now notice the optimal in all three scenarios is not the same. We managed to get the same value in these two cases. In the first one, the value was also different. The optimal cost was also different. And what ended up being optimal is not same in them. In general, it won't be. Even in this example, which is very easy, where you can just figure out by just looking at the matrix carefully, the utility matrix or the cost matrix carefully, even here the optimals are not matching. Point that you need to be carefully understand here is the information visible to the two agents matters. What they can see for sure and where they have a confusion, that matters. Right now it's a scenario with just three states, right? If instead of omega 1, omega 2, omega 3, if there were more, then the number of possibilities would increase, and hence for each possibility there is a chance that the optimal actions would not match.
In real algorithmic scenario, how do we develop for this? Or there is a ecosystem for this?
uh,
Definitely in algorithm side, I won't prefer to tabulate everything and do.
I actually don't know the answer to that. This is a game we're dealing with right now. People
Mm-hmm.
tend to not go for making algorithms to solve for these games in a faster way. You can
Okay.
write down these things and these can be calculated faster and you'll get the answer faster. But typically, the amount of work you'll have to do to write that script
Yes, yes.
would be too much as compared to how much time you'll have to spend in actually solving it. So it's uncommon. I am not aware if there are any tricks of doing this. Since this is a problem with team, this is still easier because it's either minimization of both or maximization of both. They have the same utility, same thing that is getting optimized.
Mm-hmm.
In non cooperative settings, even that won't happen. So, my guess is it's taken as just an optimization problem, and that's about it.
Okay.
It's typically solved for simple cases. Then they might, depending on what exact scenario they have, what exact formulation they have, there might be algorithms depending on cases. But in general, I am not aware about it.
Mm. Because game theory point of view, based on my experience, it's like event happens. To explain that event happen, people use game theory. They don't have before event happen. They don't calculate what is cost. I no no maybe I need to check.
Okay, I'm not sure if I understood your statement.
No, basically some event happens and something minimum cost occur. Then they will apply game theory. Say it's a Nash equilibrium because of this factor that factor. But nobody model it and then come up with this. You have to do this as of now. Simple model, yes. We don't have
Uh,
generalized version.
because generalized version may be extremely cumbersome. See, just doing it for two agents is not easy. Even if you should just fill a table, you have to be very careful what is known, who knows what, how are they using it, and then solve, which is still a little bit of work. And for every scenario, it'll change. So, I'm not sure if people are thinking about creating algorithms for solving such things.
Okay.
Okay, so with this, we have looked at the second scenario. So we looked at the first one, perfect information, perfect and identical information, then imperfect and identical information. Third is, what is this third one? Oh, not
non
identical.
non
Non-identical. Right. So now for non-identical, let's just take one case because only doing one case will take time. And then we'll do the last one. Okay, so the scenario we're considering is the following. Remember, so far we were quite lucky that we didn't have to do much calculation. Typically, that won't be the case. Oops. Okay, now this third case is the scenario when the agents know different things. Now they have to be careful in their respective policies. They have to do the whole process quite carefully. So we've taken an easy scenario for the time being. The scenario is agent 1 knows nothing. Knowing nothing means y1 is actually sigma of all of them together, meaning it can't distinguish between any of them. So the only actions the first agent can take is just U or D. It has no cases to consider because it can't see the cases. So it's only going to take two actions. So that part is the simple part. On the other hand, U2 can see everything clearly, can distinguish all of them. That means how many policies would be here? So that's two policies for this one.
16 again coming, because 8 will be on the second agent and 2 will be first agent.
Are you saying it's 2 to the power 3?
Uh,
Uh, I would have
no,
thought it's 2 to the
2 to the
power.
power 4 itself is coming. 2 to the power 3 itself will be the agent number 2 policies.
I'm
Like,
asking only for agent number 2 right now. Yeah, yeah.
perfect,
For
perfect,
agent
yeah,
number 2, there are 8 policies.
8 policies.
Overall, right. Overall, there are still 16. So let's make the table. We'd write it in this order, okay? Whatever policy is for this one, then this one, then this one. So, for example, it could be LLR, for example. Okay, I'll write it as a tuple. I'll write it in that exact form. So, the options are UD is the easy part. Here we have LLL.
This DLLL is very interesting.
Okay. At this point, I have no idea. I can't think of a trick here, so we might have to actually solve all of them. So, which one are you saying is interesting? Let's look at that. This one, this position.
DLLL, yes. Point 4 is the cost.
Okay, let me confirm. This is 2 times 0.2, 0.4. Hmm, okay. I guess. Yeah, that looks correct. What about the scenario with L
D L
R
L
L D L R L? Okay, this one, or even R R L.
R R L
Yeah.
or this R L L. R L L is also 0.4.
Okay, so R L L is R L L refers to this scenario. L L. Okay, yeah, that's point 0.4. Good.
Yes, we can fix L L wherever L L is there. Now gone.
Mm. There were two scenarios with L L. So, what about this scenario? For the middle one, there is a R.
Okay.
This one R, this one L. Oh, sorry. So, try these two. Okay, try L R L. 0. I think that's again point 0.4.
0.4. For D case 0.4. For U case it's going to be 0.8. No, no, more than that.
No, no, I'm not asking you to do for UKs.
Okay. Okay.
You would come out to be point. Right. You might come out to be point 0.8.
Very high. Okay.
Now try. Yeah, try these ones. Just confirm these two.
Which one? D R R L.
This one. LRL. It is. Wait. Were we making some mistake? Oh, I think this is not correct.
Yeah, 0.8 it is.
Right, right, right. Because this one is not going away. This is still there. This one should also be then point 0.8. Try this one then.
Which one?
ULRL.
U L R.
So ULRL, this is 0.
Yes, gone. R will be 0.8.
U
Then L will be, no,
here
it will be
R.
high.
Right. Here it's still point 0.8. Okay, this is gonna be much larger.
Yes,
So
yes, yes.
we're not bothered.
Yeah, because DL combination was good for
Hmm.
U2 omega 2 omega 3. DL combination we have explored.
So it looks as if this might be the minimum.
Kinda.
Hmm. It looks that way. The only way to confirm for sure is to write all of them and check. This also would be point 0.8, right?
Yes.
Okay. Then we are sorted. Then it's going to be this only. So there are two possibilities. Okay. So this was the scenario where one guy didn't see anything and the other did. The next one is going to be even more complex. There we might actually have to solve more. So let's try the last one. Which one did we? What was the plan? Okay. Now, how many policies for each of them? So, how many policies for Y1 and then, I mean for agent 1 and agent 2. So, Y1 has two options, meaning there'll be 2 to the power 2 policies. So, there are 4 policies. And similarly for the other one also. Let me stay consistent. So far, every time there was an oblique, I kept it in the beginning. The other one was here. Okay, and it's in the same way that I'll write. So if I'm writing for U2, if I'm writing LR, then it means L is for this one and R is for this scenario. Similarly, if I'm writing UD, then U is for this one, D is for this one. Okay, so let me write it out. U. Hmm. Now the policy is a bit complicated. Now let's look at U. Let's look at agent 1. Agent 1 doesn't know between omega 1 and omega 2, but it knows if it has seen omega 3, meaning it will either try.
In this case, we need to tabulate only.
Yeah. There's no way out.
Yeah, for agent 1 is messy.
Agent 2 is also no less. Agent 2 might be. Okay, agent 2 has this.
Yeah, only U option. Agent to stick with the U.
Agent 2 will stick with L.
Um, yes, my mistake.
Agent 2 should stick
Stick
with
the agent
L.
L
But L
because
is meaningful if agent 1
choose U.
chooses.
Okay, we'll elaborate on it
Yeah,
later.
there's no choice here. This needs to choose D. Okay, so let's try a few of them and then we'll just leave it. You can try filling it up yourself and see if you can make any sense out of this one. Okay, I don't want to spend all the time doing this, so let's just take one or two examples. So let's take U. Can it really be U? 1 and 2. U is a bad one. Okay, maybe let's look at it this way. Yeah, no clue. Okay, let's just do one or two of them. UD.
UDLL is interesting.
Okay, let's try what happens. This is confusing. So, this is L with. Okay, what has happened in omega 1? In omega 1, they will choose U and L. So, here this is what they'll choose, correct? That's 0. In omega 2, it's going to be U and L. That's not good. Omega 3 will be D and L. Okay, so this is coming out to be 0.8. UD and L. You just need to see if there can be something with zero point 0.4.
If we try DDRL,
Okay,
I think this is zero, complete zero coming. DDRL.
I I'm not sure if there might be a 0, but okay, let's give it a try. So DD means in for omega 1 we would get D and L. uh, uh, D and L is this.
Then sorry, then DDRR.
Okay, okay, you want to try DDRR. Okay, for omega 1 that is DNR, but DNR is this. That'll give you
It's,
zero point 0.4.
I did mistake. Yeah.
DNR here will give you again zero point 0.4. I don't think it's DNR. This is giving you zero point 0.4 into it's 0 0.4 into what, 3, 1.2. Yeah, that's definitely much bigger. That's not gonna be it. This might still work. Let's try this one. No harm. You can't anyways make a guess, so
It's 0.4 plus 00.
it's 0.4. It's D and L, so it's this one. Hmm. I think this might be the smallest. There might not be a smaller one. DDRL, right?
Yeah, all 00 is not looking in way possible.
Let's look at UURR. Does it turn out to be? Yeah, this one is going to be zero point 0.8, right?
Yes, 0.8. And you are safe here. 0.8. Thing is, when you go with a lower for omega 2, the problem of agent 1 is coming up because agent 1 can't distinguish omega 1 and omega 2.
Hmm.
So whatever he decides for omega 1 has to be for omega 2. And
Yeah.
interestingly, wherever omega 1 is 0, omega 2 is 2.
Maybe this one?
Then it means dr. Then if we go this side, it should be dr.
No, no, I'm not saying.
Like D, if we choose D, then agent one has to choose D for omega one also, because it can't distinguish omega one and
But
omega two.
agent 2 can choose differently, right? Okay, so what about something like this? Uh, the amount of translation that needs to be done, written it in a
Yes.
very clumsy manner. Okay, so it's D. Okay, the first one is D. Okay, what about DUR? What should it be? What should be the last one for R? RL or RR?
Should be R, but if you put R, then point 8 will come.
So you're saying DURR is what?
Point 8.
Is it? So DU means this is D. Here we're choosing D, and here we're choosing. Okay, both of these are D. Ah, oh, okay. Because of this. Oh, because of this.
Yes.
Hmm. Then this might be the smallest, but yeah, at this point I can't confirm. It the way this example is, zero may not happen in scenario with non-identical imperfect information.
Yes.
So zero point 0.4 seems like a good value. Okay, maybe you can check this one more carefully. Try filling up the rest of the table and see what happens. Okay, so what we did right now was take an example between two agents and three environmental noise terms. Each of those agents could take two actions each, and then we looked at what happens to what is their optimal strategy and the optimal cost in these different scenarios. For the case of imperfect and identical information, we took all the cases. For non-identical, we took one case and we stopped at that. There are definitely a lot of cases possible, but we didn't go through all of them. So for example, here, if both of them, if their y observation gives them two things, this or not this or not this, there are still scenarios that are possible. So in this case there are 6 minus 9 minus 3, 6 scenarios possible. We didn't go through all of them, we just went through one of them. If you want, you could try the other ones and see that the optimal policy may not be the same. The cost also may be slightly different. But nevertheless, one key thing that you could notice from all of these was when you were in the perfect and identical information scenario, the cost that you got was actually the minimum cost that you could have gotten. When the information became imperfect, the cost was either more, for example, zero point 0.4, or exactly the same. And similarly, with the third scenario, cost was either more we didn't find the cost to be 0, so most likely it's more. It's non-identical and imperfect. With that, for 3 and 4 we may have already found the optimal, but it's still fair to fill the whole table and check. Okay, now let's go back to what else was done in the lectures. Hmm. Okay, so after talking about these team games, the videos talked about two kind of optimalities in team games. So to talk about that, we can focus on the optimization problem, and we can convert this optimization problem into two optimizations: minimize gamma 1 and then minimize gamma 2. Like, can be done one by one after the other. And if we're doing that, we could solve it, like solve the inner one first, and to solve the inner one first, fix the value of gamma 1 or gamma 2 and then continue doing it. Hmm. Right. And because from here to here it's just the property of expectation, that is all that is used, then the inner argument here, this will be a function of the y2. And because it will be a function of y2, we could interchange the expectation and the minimization. And notice when we are doing this, we are keeping a value of y1 fixed and then finding the optimal here. Once we have found this optimal, then we are changing the gamma 1s or y 1s. So for a given y1 or for a given gamma 1, this is like a best response for the certain scenario. So this is leading to a situation where we may get best responses for all the agents involved and still not be able to get the complete optimal, which is what happened in Witzenhausen, if you recall. We saw that the best response for a linear strategy by one controller was a linear strategy by the other controller also, but the the two linear strategies taken together was still not optimal. It was possible to find strategies which were non-optimal, which were non-linear, that behaved better than linear strategies. Okay, I am gonna not talk about this particular scenario. If you have doubts, you can ask. Otherwise, I'll skip this. I'll just go to the LQG part. So here, this is taking the information in a slightly different way. Instead of having it as information, like knowing whether the agent knows the exact value of uh, the xi or not, that's what we've been talking about so far. Another possibility is maybe it knows a linear combination of it or some scaling, some function that acts on it. If that is the case, then there can be a joint distribution on, sorry, this environment and this correlated observation of xi, the z this time, and this can be incorporated in the same example. The number of strategies would depend on how you've defined it. Okay, any doubts in this particular example that sir talked about?
Yeah, no, in this, that merging of information is clear, but there was a point where we have to define the joint probability.
Here, here.
No, no, down, in the cost, we have to merge. In the cost, the down denominator probability of p omega 1 plus omega 2 is like much more lower. Like,
I remember
okay,
something like that was there, but I can't find it.
it
Oh,
was
I think that was this one. This is still the case with imperfect and identical information. Sorry, if that is the scenario, then whatever is the part that is not known, like if you can't distinguish between omega 1 and omega 2, you could club that information together.
but this direct expression denominator, I can make sense of above. It just weighted sum of
Hmm.
the cost
Hmm.
down divided by this from where
Okay.
it is
Do
coming.
you recall what we are actually interested in is the expectation?
Mm,
Expectation of L, whatever.
mm,
Right? Which means ultimately, once we write this, we will be multiplying it by the probability of this. We're defining it as a new event. This or this. Omega 1
mm.
or omega 2. We're defining it as a new event, and that's it. So, what will actually happen is, okay, let me write that here only.
So that mathematical expression or basically means like plus sign makes sense if both are independent.
Hmm. So, what I'll write now is I'll take the probability of omega 1 or omega 2. Right? It's this event LAB W1 slash W2 plus what I actually know, which was W3. This is still the same as what we had before. It's
Correct.
just jugglery, nothing more than that.
Okay.
They brought it down here because they're gonna cancel it with this term.
Oh,
But it takes the form that we want. This is as if the two agents, it's no longer a two agent problem. It's as if this is taken as an event itself,
mm-hmm.
and that event is known. The probability of that event is known. The loss of that event can be calculated. So it's actually a situation with single agent, complete information.
Okay. So that cost somehow we algebraically we represent into combined
Hmm,
information form.
that's all.
Okay.
Okay. So then, where are we? Okay. Okay, right. So now there are two types of optimalities. One is what we have been talking about so far, which is team optimal, meaning that the best policy that is being chosen is for all of the agents at the same time. And what this means is that the say suppose this is the best policy, then the cost function for this best policy would be less than or equal to if you change any other policy, if you change the policy of any agent. That is team optimal. That's like finding the global optimal of the problem. The other kind of optimality solution is what is called as person by person optimal. And person by person optimal, the policy profile is set to be person by person optimal. Not team optimal, person by person. If we're only doing this much, you're keeping every other policy fixed, policy of the all the other agents is fixed, and only you're varying one policy, which is for example your own policy, which is like you're making unilateral deviation. And person by person optimality says that unilateral deviations will not improve the cost. It could keep the cost same, but it will not improve it. And this is true for all gamma i's and all I for all the controllers or all the agents. Now you can notice the way these two conditions are defined, they have some relation with each other. The easy relation is, suppose we found a team optimal policy profile, as in for all the agents at all times, if there are times to be considered, if all of that is already considered, okay, then that will by default be a person by person optimality, because there you could fix the other ones to be the policy from this and only change one of them, and it'll come back to the same profile as before, or from the same set of optimal team policies. So what this means is that every team optimal solution is person by person optimal. The converse is not true in general, as in if something is person by person optimal, it may or may not be team optimal, because this is similar to a unilateral deviation. That some unilateral deviation won't give you improvement in the cost, but here we're not talking about unilateral deviation. It's everybody finding their optimal policies together. So this is more like a global optima you're finding with respect to all the variables. So all the variables meaning all the gammas, and you're doing it together, you're doing it at the same time, you're not fixing one and then finding and then trying to go the next step. But there is a theorem which says, if you're in static team game, of course, if your loss function is strictly convex and continuously differentiable in the actions for each uh, environmental noise, then person by person optimal is also team optimal. Okay, so if this is satisfied, if this bunch of conditions are satisfied, then the claim is these two are actually going to be the same, because we already know if something is team optimal, it will be person by person optimal by default. Now we are saying if something is person by person optimal, that will also be team optimal. So they will have the exact same solution space. In scenarios where your loss function is strictly convex and continuously differentiable with respect to the action profiles.
This is similar to, like, it's just a thought, okay? It's just similar to when you have a convex function, the minima itself is a global minima.
Yeah,
It's exactly same.
it's exactly same. So okay, so one very naive way to think about this would be, think of a bowl, a convex bowl. Okay, think of it in a three dimension. If you're able to think in higher dimensions, that's fine enough. Now, team optimal means you're trying to find the minima with respect to both the variables at the same time. So you're looking for the actual minima. That's what you're up to. So fair enough. In person by person optimality, what you're doing is you're fixing a strategy for the other one. So fixing a strategy means, suppose you have these two planes, this plane and this plane. You're fixing a plane here, and then you'll have a parabolic curve or something, some convex function here also. There you're finding the minimum. You found a minima, then you're like, okay, now let me change this. Let me change this one, and then you keep on moving. So if you continue doing that, if it is a convex bowl, you will end up at the same point, which is what this is roughly trying to say. Obviously, I can't give more intuition than this.
Yep.
So, one scenario where this is observed and used a lot is LQG team games. Okay, before even we go to LQG team games, notice we are talking about strictly convex and continuously differentiable, meaning these U's have to be real numbers. The U's can't be discrete. Then we can't have a meaningful uh, mm, sense of these words. Continuously differentiable will not be a thing. Okay, so let's now talk about this LQG team. I'll not talk about much in detail about this because in one of the tutorials, while solving for strategies, I think we already solved how to get the optimal strategies in case of a team game, a team LQG game. So I'll not go through that part again. The arguments in the videos this time were slightly different, but anyways, they lead you to the same result. Okay, so the problem is this way. Suppose you have n agents, so you have the action from u1 to un. Then the loss function is something which is quadratic in u, where q is positive semi definite, and the this xi is some Gaussian. This can be thought of as some state of the world, some environmental noise, which is what is present in the loss function also. And the observation of the agents, the yi's, are only dependent on xi. And here the dependence is in a correlated form. It's a noisy dependence. It's not knowing the exact value, it's knowing some of it. So there's some h that acts on it, so some linear combination. And we could assume that h is not invertible, hi, any of the hi is not invertible, and that the dimensions, it's a rectangular matrix instead of a normal matrix, and you can say that okay, if that is the case, then it should at least be full rank, a row full rank matrix. So here the ui's would depend on the strategy, the policy gamma I. Since L is strictly convex in U, because it's a quadratic function, you could always complete the squares and make it more like a mean square error estimation with some other terms which anyways we're not going to be affecting. And this is also continuously differentiable for all values of xi. That means here the person by person optimality would give us the team optimality. So all that remains is to find out what is person by person optimality, and this is exactly what we had done last time. And there we had found that the person by person optimal for LQG problems with this kind of an information structure was linear strategies or linear policies. So they were linear in this uh, yi. Mm. So with this, we've covered most of the topics. One thing that was talked about was the Witzenhausen's example and how that is somewhere in between pure communication and classical information. But because that's more related to the next week's lecture, so I'll take it next time. So, any doubts so far?
No, I said.
Okay, right. I had one example. I forgot about it. So consider a situation like this. So this is a very simple example. There's not much to it, but if you want to get a sense out of the meaning of team optimality and person by person optimality, you could try it out on your own. So let's say we're taking a scenario with the state of the world xi as having some. It comes from R3, and it's actually sampled from a Gaussian distribution with identity as the covariance. And let's say we've taken some values for these matrices QS, and these eta A, eta B basically refer to YA and YB. AB are like the agents. So this is agent 1, this is agent 2. This is agent, or maybe more like Alice and Bob if you prefer. Okay, so you could try finding the person by person optimal policy in this. Do you remember how to do that?
Not completely. I need to go.
So because this is a simple this is a simple scenario. All you have to do is where is the form? All you have to do is write it out more carefully, maybe specific to each term, specific to UA, UB, or whatever actions, however you want to define it. Write it out specifically. Then you're just supposed to minimize this quantity, right? You're taking the expectation of this and you're minimizing that quantity. So if you do that, if you write it out carefully, convert the matrix form into a simpler version, you'll see some nice patterns showing up. That's how much I'll tell you. But yeah, it's relatively easy. And then since you're just supposed to optimize it, minimize it, you can just take a derivative. And when you do that, you can find what that gives you. It'll give you the needed values of gamma A and gamma B. So here in that sense it means I'm referring to this as this is what I'm referring to as gamma, okay? The vector, the linear vector. This is abusive notation, but because we know it reduces to something linear, let's just use the same symbol. Okay, so you can try out this example. This is just putting the numbers and solving for it. It will give you some feel for what is happening here. Or if you are comfortable, write a code to do this. This is an optimization problem, so for this kind of an optimization problem you can easily write a code.
Okay.
In fact, this is a LP, so standard LP solvers will work. Alright, any doubts so far?
No.
No? Okay, then let's quickly recap what we did today. So today's focus was on team scenarios, and specifically we didn't even bother with what happens to time because that can be incorporated in the number of agents itself. And the examples that we took were with just 2 agents because that's how much can be solved on paper. More than that requires a lot more effort. So we saw one example with discrete actions and environmental noise, and the environmental noise had some probabilities, some distribution on top of it. So we saw how to find the optimal policy in these different scenarios. The case with perfect and identical information, imperfect and identical information, one case with imperfect and non-identical information, this another case with imperfect and non-identical information, but where both the agents had some non-trivial measurements available to them. And we saw the example that we took was a little easy, so we didn't have to solve the whole of it, fill the full table of strategies and the J values for it, and we were able to pinpoint why that's not needed. We were able to get the optimal value and the optimal policy in most of the cases. These two may need verification, but anyways, we managed to do that. Then finally, we talked about two types of optimality. One was global optimal, similar to global optimal, which is called team optimal, and the other was person by person optimality, which is the same as saying no unilateral deviation can improve the cost. And then this was just one example that I gave that you could try on. Mm. Hmm. And we saw one of the relation between person by person optimality and global optimality or team optimality is that every sorry team optimal policy will be person by person optimality, that person by person optimal, that's by default. It's the converse that can happen in scenarios in static team games where the loss function is strictly convex and continuously differentiable in the use, in the actions for all the agents and for all the environmental noise. If these conditions are satisfied, then person by person optimal solution will be the team optimal solution as well. And this is true, for example, in LQG games. LQG team games to be more specific. Okay. With this, we have covered this week's tutorial. We can pause here.
Actually, I don't have question for this, but I have something to show on this course related thing.
Okay, tell me.
Share my screen.
Yeah, sure. Um, Let me know if you're not able to share.
Yes, I'm able to share.
Ah, okay, perfect.
Yes, recently I went through this Spectrum, that every month Spectrum release this IEEE Spectrum basically release magazine. So I usually read that. This time the robotics division they have published this line. So
Okay.
idea is like robots do better when they can fear. But the line this is I felt it's very similar to the course which I learned. So the professor Alexandro Rezzo he has like claiming that they emulated the fear response using a controller.
Okay, one second. Let me read this.
Hmm.
Uh, how have they, first of all, how did they quantify fear? What did they use for that? Is there any mathematical version of it, or is it just a statement that they're making?
As of my statement, the paper I need to go through.
Ah, I see.
Mhm.
Okay. So, fear is closely related to self preservation and rapid responses to danger. Okay. They emulated the fear response using a controller based on RL. Okay. It's the ping statement you want me to focus on, right?
These two students somehow it's like in that same thing which we are discussing. Take the input based on the state, but I think they are not taking state. They are taking working on information and then connect with the fear. Like whatever I learn in this course, I'm able to connect this. Like that's what.
Yeah, see, this course was mostly about control. Once a controller is trying to learn the distribution,
Mm-hmm.
that's a RL problem. Control is
Okay.
like MDP planning, if you're aware about the terminology that people in RL and so on use. It's just
Mm.
MDP planning. You are trying to optimize what would be the best situation if you knew everything about the MDP
Okay.
or the stochastic control problem. If you knew everything about it, then if you didn't know the dynamics or you didn't know the transition probabilities, for example, that's what you would be trying to learn in a RL setting. So the learning is learning the distribution, the transition probabilities, for example.
Oh, okay, 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 okay.
So this is like the next level thing. RL is like the next level thing to stochastic control.
Okay. So basically, like controller don't know everything. Based on RL, it will try to learn the transition capability and then take decision.
Hmm.
Okay. So still I need to spend more time to understand this concept.
Uh, can you look into it and tell me, are they trying to do it by modeling the rewards of the environment in a smart way, such that if there is a difficult situation, the agent should not take so and so action but take so and so action, so the reward is skewed that way? Is it
Okay.
done using the reward, like the designing is in terms of the reward, or what? Like, how did they model fear? That's what I want to understand.
Okay, then
Okay.
I will go to the paper. In the
Yeah.
next week, I can show
Sure, sure,
my
sure. Perfect.
understanding.